can, of course, figure out what must balance this. So we go ahead, and this is your classic two equations, two unknown structure. We just made sure that the two unknowns weren't intertangled. We made sure to just have one of the unknowns pop out of one of the equations, the torque equation, and put it in the other one. And you can find NA ends up being 735 newtons. So we've now accomplished the numerical solution to the problem by finding out the forces that each support must lend. So we found that this, if this is 490, this has to be here 1225, and this has to be 735. There are no other pairs of forces acting at the locations that we've given that would satisfy both that the net force was 0 and the net torque was 0. Now you might say, well, you're saying that these are the only two forces possible. Why can't you take a Newton away from this and take a Newton away from this? If you take a Newton away from an upward force and you take a Newton away from the downward force, wouldn't the forces still cancel? Sure, of course. But the torques wouldn't anymore. Okay? So if you said this was only 1224 newtons and this was only 734 newtons, the forces would still balance, but the torques wouldn't. If I pick the pivot here and I compare the torque by these two, this torque would not be enough to cancel off the torque of this. Okay? So we have been able to successfully, by making sure that the two equations are satisfied, net force and net torque, we've been able to narrow down the values for these two forces uniquely. Okay? Are there any questions on that before I show you briefly how you would do it with another pivot? Okay, so again, I just happened to take the pivot at the very end here. It's a good exercise to try to look at it with a different option. I guess I'll do that over here, just so I can refer back to my original pivot. So there would be nothing wrong with a different pivot. Let's say, for instance, I pick the pivot to be at the V force. So if I were to do a sort of rotational free body diagram, I would omit that force because that's now acting at the hinge that I have. So I'm basically pretending now that my hypothetical hinge is here instead. So I'm going to look at the competition between the gravitational force, which would try to rotate it this way, and the support from the end, which would try to rotate it the other way. So you can see there's a competition, and I have to make sure that neither torque wins. So I'm looking at a competition between this force and this force. So I go ahead and I sketch out the circle here. Force A, which way does that want to rotate it? So plus or minus? Plus, counterclockwise. So the torque of A is plus. And how much leverage does it have? 2 meters. Remember, that torque used to be 0. Now it's not. Everything flows from the pivot. So depending on your pivot choice, the torque could be 0 or not 0. The force of gravity would want it to rotate the other way. Again, I can trace it around the pivot. So that torque will be negative. It was negative in the previous one. It's negative now because in both scenarios it happens to want to rotate counterclockwise. Again, I do a head check, and I see that these torques are opposite directions, and that's good because the net torque should be 0. So the net torque might still be in the clockwise direction, but the leverage has changed. How much leverage does this force have now? It only has 3 meters of leverage from the pivot. So notice everything flows from the pivot choice. Does the force of gravity have a leverage of 5 meters or 3 meters or 0 meters? Well, it depends on the pivot choice that you want to use. So convince yourself, go through this, and convince yourself that RANA has to come out to be RGMG. Again, these two torques have to cancel out. And in this case, you'd be solving for NA. NA would pop out first. The torque of gravity, well, this is 490 newtons. The force hasn't changed. That's given. Now the leverage is 3 meters. It's not as much relative to this new pivot. This has leverage of 2 meters, and you can solve for NA. Well, guess what? NA is going to come out to be exactly the same thing as it did before. If you solve this, you'll get NA is 735 newtons. And if you want the other one, there's no need to set up a whole second torque equation with a different pivot. Just use this, right? If you know that these two have to add up to NB, that's how you get NB. And of course, NB you'd get 1225. So there's no wrong answer for pivot as long as you are careful in setting it up. But notice here that NB popped right out of here because of the way I chose the pivot. Here NA popped out. If I chose this pivot here, I'd have both of these unknowns coming out of my torque equation as well, and I'd have to do a little bit more math to get both values. Try that if you want. It works out just the same. You can also go back, and that seesaw example I did last time, that looked like this. I had two forces of gravity and a normal force. There, seesaw has such an intuitive pivot so that maybe you didn't blink an eye once I chose it in the middle, but you can also do that with other pivots. You can pick this to be the pivot and look at the competition between these two torques. So every one of these things is multiple practice problems in one. Just pick a different pivot and make sure you can still get the same answers. Okay, are there any questions on this? Okay, so this business about picking whatever pivot you want, it only applies to static equilibrium problems because once the object is in motion, you need to use the actual pivot. Okay, so in static equilibrium, when the net torque is 0, you can use any pivot. But if there's actual rotation, or generally any kind of motion, you have to use the actual pivot. Usually easy to find because it's the point that everything else is going around. So this is where we are finally ready to release the restriction that the net torque be 0. We've talked about it previously, just conceptually, this idea that net torque leads to angular acceleration, but the connected glue is this thing called rotational inertia, which we now are going to go ahead and tackle. So that'll be the last thing we introduce for homework 9 and exam 2. Are there any questions before I tackle that? Okay, so let's move on to rotational inertia. So let me remind you again what it is. If we have F net equals ma com, to connect how much net force an object feels from its environment to how much its center of mass accelerates in response, we of course need to know the mass of the object, which is some measure of how stubborn it is to changing its motion. Now there, the linear inertia, that begins and ends with a single physical property. If you know how massive something is, you know how stubborn it is to acceleration. If you apply a net torque to something, and it'll cause an angular acceleration, but how much or how little has to do with this thing here, which is called the rotational inertia. So that's how stubborn it is to changes to its rotational motion, how stubborn it is to angular acceleration. We have to kind of go slowly on this because the rotational inertia has three different things that go into its determination, so we need to consider what those might be. So let's try it. Let's start discussing what rotational inertia depends on. I depends on, and I'll list the three factors. 1, 2, 3. So the first one, just good old mass, okay? So that's the first one. Mass matters in the linear or translational world. Mass also matters here, okay? The difference, of course, is that this is where the story begins and ends over here, whereas that's only the beginning of the story here. So this is analogous to the linear quantity, linear motion, and these two are not. They are rotational only. There are two additional factors that we don't ever have to consider in the linear world, but we have to consider now. But for the time being, let's go back to mass. Mass makes things more stubborn to changes of all kinds. I'll tell you what the other two are for the moment. Mass distribution and axis of rotation. So it's going to turn out to matter how mass is distributed and then how you rotate that object. So the reason I just mentioned the other two before I start is because I'm going to try to hold the other two the same whenever I'm looking at one of them alone. So if, for instance, I'm just looking at mass, I want to pick a mass distribution and axis of rotation and then keep those fixed. So I'm going to pick a mass distribution that's a sphere, and I'm going to rotate them both through the center of mass, so assuming that they're uniform spheres. So that way, I can focus in on just mass. I'm going to say that this one has more mass. So they're two identically shaped spherical objects, both rotated through their middle. The only difference is one might be, say, made out of styrofoam, and one might be made out of like lead or something like that. So there's a big mass difference in the two. I don't know how to draw that. This is more mass. I don't know how to draw that. It's more mass. Okay. So imagine I had both of these things in the room. I had this gigantic styrofoam sphere, and I had a big lead sphere, and I tried my best to change their rotational state. So I went up to the styrofoam ball, gave it some torque, and I went up to the lead sphere, and I also gave it some torque. Now obviously, just because I apply the same torque to them doesn't mean that the same thing happens to both of them. We're going to find that the one that has more mass reacts a lot less, right? Because it's more stubborn to changes. So this one, for the same net torque, it has far less angular acceleration, so therefore it must have a higher rotational inertia. It's more stubborn to changes because it has more mass. Okay, so we're looking at I is larger, so alpha is smaller. This shouldn't be a shocker because more mass makes things more stubborn to any kind of motion. It makes them more stubborn to accelerate along a straight line. It makes them more stubborn to rotate, go faster in a circle. So that's my first conceptual takeaway. If you have something that has more mass, it also has more rotational inertia. So the blanket statement there is that mass makes things more stubborn to change their state, whether that's linear or rotational motion. So that one hopefully isn't a big shocker, but the other two have no analogous behavior in the linear world. So from here, let's go to mass distribution. So here's what I have. I have these two wooden blocks and a meter stick. So this is my mass, the amount of mass I'm going to work with. So this has a certain mass. And that's where the story begins and ends if we're talking about the linear motion, right? The only thing I need to know is how massive it is. So if I wanted to lift this barbell into the air, how hard that is simply how much mass it is, right? I don't have to worry about the shape of it, okay? But rotationally, let's try it. If I take that mass and I distribute it in closer to the pivot like this, let's try to get it around the center of mass, so roughly about like that. I get a sense of how stubborn it is to rotational motion. So I can see, I give this some torque, I see how stubborn it is. And then I move the mass out, and I find that it's much more difficult to change its rotational state. So I've added some stubbornness in the rotational world. Again, if I'm moving in a straight line, that doesn't matter. But rotationally, I can change the stubbornness by changing the mass distribution. You don't need a fancy physics demo here of a meter stick and 2 wooden blocks. You can just try it with your own body. Try torquing yourself like this and like this, and you will notice that there's a significant difference. You feel more stubborn when your mass is distributed further up. Okay? So, if I sketch that, compare this, and then redistribute the mass further out, I will also find, same deal, this one, I guess I should kind of, for the same net torque, I get less angular acceleration. So must be more stubbornness, more rotational inertia involved. So that's my second takeaway. When the mass is further out from the pivot, that will cause a larger rotational inertia. That only matters, of course, for the rotational world. Okay? It's equally difficult to lift in a straight line, whether the mass is distributed closer to the middle or out on the ends. This is rotational only. Okay? So there is no analogy here. This looks confusing. So this is analogous to linear, and these are rotational only. So there's no analogous behavior in the linear world. Okay? So that's factor number 2. And then finally, factor number 3, this is, to me, the weirdest one of all, okay? Because the first two, as far as the mechanics go, establishes the object completely. So what is an object? It's the amount of mass and how that mass is distributed. You could still talk about other properties like is it red or blue or something like that, but as far as the mechanics go, the entire object is established when you say this is the mass of it and this is how that mass is distributed. But there's still something left. So if I take an object, let's say it has this mass and this distribution, if you try to angularly accelerate like this, get a sense for how stubborn it seems like that, and then I can try it again like this. So I've moved the axis of rotation. And I find that that's more difficult. It turns out that the way to give the less, once you've established your mass and mass distribution, the way that you can angularly accelerate something so that it's least stubborn is to do it when it's going around its center of mass. So it's the easiest to change something's rotational state when it's rotated through the center of mass. If you try to take it through another point, another axis of rotation that's further from the center of mass, it's even harder. Okay? So we have the exact same object. We rotate it through its center of mass. The rotational inertia here is going to be minimum. So not 0, it still presents some stubbornness, but not nearly as much as if I change the axis of rotation to somewhere else. So I take that exact same object, I try to draw the barbell exactly the same length, and I rotate it like this, not through the center of mass, and once again, I find that it is more stubborn to rotational change. So my third conceptual takeaway is that if you rotate further from the center of mass, so if the axis of rotation is further from the center of mass, that will also increase the rotational inertia. It will make it more stubborn. Now the reason why I think this one is the weirdest one is because factors numbers 1 and 2 here, these are what I'll call intrinsic to the object. They make up what the object is. What is its mass and how is it distributed? But this one is extrinsic, which is to say it's not really a property of the object at all. It's a property of what you decide to do with it. What axis of rotation are you going to use? If that doesn't seem weird to you, let me point out, if we had that behavior in the linear world, how bizarre that would be. That would be like saying, if I want to push a mass this way, it's 5 kilograms, but if I want to push it this way, it's 3 kilograms, right? That's crazy, right? Mass is mass is mass, no matter what you do to it. There's a certain stubbornness that something presents, which is inherent, because mass of an object is inherent. How stubborn something is to acceleration is an intrinsic property. How much mass does it carry? But I'm literally telling you that you have the exact same object. You rotate it like this, it presents one rotational inertia. You rotate it somehow else, it presents a different rotational inertia. So the rotational inertia of an object is not something that belongs to the object. It's what the object is constructed with and the particulars of how you decide to rotate it. You can rotate something in a given way, and it presents more or less rotational resistance than if you rotate it through another axis. Again, if we had that kind of analogous behavior in the linear world, the same object would be 5 kilograms in some problems and 3 kilograms in another, which is, again, there's no behavior like that. Okay. Are there any questions on that before I move forward? Okay, so those are the 3 conceptual checkpoints, and they are extremely useful when you're head checking your answers or comparing things to just know what goes into the rotational inertia, these 3 factors. So that'll really help us as we go to the computation. Now obviously, if you want to talk about the rotational inertia of something, you have to talk about narrowing down all 3 of these factors. What's the mass? How is it distributed? What axis of rotation are you going to use? So I'm going to pick the very simplest item to start with and find the rotational inertia. So this is going to be the rotational inertia of, and this is, by the way, how we inevitably end up doing it. We don't want to describe these 3 factors because it's going to be a full paragraph, so that we can say, what is this mass? How is that distributed? What's the axis of rotation? We use the picture is worth 1,000 words. So I'm just going to draw it for you. What's the mass? M. How is it distributed? It's going to be a point mass. How is it rotated? Well, if it's a point particle, there's nothing to rotate if you just spin it on itself. So I'm going to throw it on a thin rod and spin it along in a circle. Okay, so that's my first rotational inertia. I'm going to find the rotational inertia of a single point mass rotating around a pivot. So how am I going to do that? I'm going to, of course, apply a torque and see how it angularly accelerates, and then whatever the multiplier is must be my rotational inertia. Okay? So I'm going to figure out what is in the front. So let me show you how we do that. First, let's apply our torque. So I'm going to exert a force on this mass, like so. Oh, I forgot to give you what's the radius of the circle, so the radius is r. So I'm going to apply a force tangentially to my mass. Why tangentially? Well, if it was some random direction, I'd have to throw out the component that wasn't tangential anyway, right? Only tangential components can make it go faster or slower in a circle. So tangential components are what I want. So the torque here will be RF tan. Of course, F tan is normally for us F sine theta, right? So that sine theta is really for making sure you don't keep any part of the force that's not tangential. Okay, so the tangential force is going to cause the tangential acceleration. So that's something you have to consider, of course, for your homework number 8. So I know gotten several questions on the last problem, the roller coaster problem. So you have to think about, how do you get your A tan? Where does it come from? It can't come just because this is the circular motion unit, right? You have to have an F tan behind it. You have to have a force behind it to get an acceleration into that direction. Now, I don't want A tan. I want, of course, its cousin, the rotational analog, R alpha. So now I'm done.